So next one is EMF equation of transformer. So we are going to see what is the induced EMF in a transformer. So as you know, I'm going to apply an AC voltage V1 to the primary. So because of this AC voltage, I'm going to have an AC flux. So AC voltage will give rise to AC current, and the AC current is going to give rise to AC flux. And the flux is given by the notation phi. Phi is your flux. And the flux is represented as phi is equal to phi m sine omega t. Phi m sine, omega is 2 pi f, so phi is equal to phi m sine 2 pi f t. And you see that whatever input you give, that frequency will be same for voltage, current, and flux. எல்லா இடத்துலயும் F தான். Nowhere the frequency will change. That is the beauty of transformer. In transformer, the frequency remains constant. Voltage will change, current will change, flux will change, but the frequency at the input will be the same as the frequency at output of your transformer. So the flux will also have the same frequency. And since flux is an AC flux, I represent it by usual notation AC phi m sine omega t. Omega is 2 pi f, and phi m is the peak value of the flux, and f is the frequency of your transformer. Okay. So as per Faraday's law of induction, we can write the equation for induced EMF as E is equal to minus N into d phi by dt. The rate of change of flux is going to induce an EMF, and that EMF is going to oppose. For that opposing only, we put the minus sign. Okay. This equation we get from Faraday's law of electromagnetic induction. So rate of change of flux produces an induced EMF that is going to oppose your source. Because of that opposing nature of the induced EMF, I am going to put a minus sign. Okay. Minus N into d phi by dt. Okay. You know the expression for phi. Differentiate, substitute here and differentiate. So d by dt of phi m sine omega t. Phi m is a constant, bring it out. And differentiation of sine omega t is omega t cos omega t into omega. This minus sign is obviously there because of the opposing EMF. And I'm going to bring this minus sign into the phase angle. So, I can write cos theta as sine 90 minus theta is cos theta. When you bring that minus sign inside, it will become sine theta minus 90. Okay, I want to bring this 90 and minus sign into my phase angle. So I'm writing minus cos omega t as sine omega t minus 90. So this magnitude will become plus. So plus n phi m omega sine omega t minus pi by 2. So it is also an AC signal, right? So this is your peak value. N phi omega is your peak value. Okay, n phi omega is your peak value. So I'm writing the peak value separately. See here, the peak value of induced EMF is given by EM is equal to omega n phi m. So the RMS value will be peak value by root 2. So EM by root 2. So EM by root 2 will be equal to, substitute here, omega n phi m divided by root 2. And omega is 2 pi f. So 2 pi f into capital N into phi m divided by root 2. So phi f n phi m, I cannot simplify. I am going to simplify this 2 pi by root 2. If you mathematically simplify, the value comes around 4.44. So E is equal to 4.44 F N phi m is the EMF equation of transformer. Very, very important EMF equation of transformer. And you see, I will once again explain how to get the EMF equation. So we have seen the operation of transformer. You give an AC voltage, you get an AC current. Because of this AC current, you will be having an AC flux, electromagnetic induction. And one thing to note in transformer, all the voltage, current, and the flux will be of the same frequency. Since flux is also an AC flux, I can represent the flux by the equation phi is equal to phi m sine omega t. And omega is going to be 2 pi f. So this phi m is going to be the peak value, and f is going to be the frequency. As per Faraday's law of induction, the induced EMF is given by E is equal to minus N into d phi by dt. Substitute for phi, differentiate, you get this term minus N phi m omega cos omega t. And I want to bring this minus into the phase term. So I'm writing this cos omega t as sine omega t minus 90. So that this term becomes plus. And this is an AC signal. So this should be your peak value. This should be your phase term. So if you find, so I'm writing the peak value as peak value is EM is equal to omega n by m. So if you want to find the RMS value, what you should do? Peak value by root 2. So see here, Em by root 2, I'm doing omega n pi m by root 2. Omega is 2 pi f, so 2 pi f into pi n by root 2. So 2 pi by root 2 is a numerical quantity. I can simplify that. You get 4.44. Other terms as it is f into n into pi m. So this induced EMF equation will give an idea about the losses in a transformer. So assume this number of turns is constant. N is a constant term because in a device n is going to be constant. And when you're going to increase the frequency, when f is going to increase, EMF will also increase. E will also increase. So if you want to effectively transfer high electrical energy, you operate the transformer in a very high frequency. By operating at a very high frequency, the transformer can be made more efficient. Okay, the transformer can be made more efficient to operate when you operate the transformer at a very high frequency. At high frequency, the flux is also high. The induced EMF is also high. The number of turns, if you have the number of turns to be very minimum, with minimum number of turns, I can produce very high induced EMF when you operate at very high frequency of your transformer. But conventionally, you see, whatever we get at the supply in our house is 50 hertz. So we will operate the transformer mostly at 50 hertz only. But one possibility is if you operate the transformer at very high frequency, there is a chance that the transformer can transfer maximum power without having any loss. That can be done. And what assumption I make? I fix the number of turns to be constant. N is constant. If N is constant, if I increase the frequency, I can transfer maximum electrical energy from source to your load. That is possible in a transformer without having losses. And one drawback also what we have is when you increase the frequency, all the losses will also increase. You have see your core is made up of iron, right? So when current is going to flow, the iron is going to be heated. So you will have core loss, you will have skin effect. All these losses also increase with frequency. So you have to have a balance between what frequency you're going to operate to get the maximum induced EMF. See, frequency, if you operate at high frequency, induced EMF is maximum. But what other cases, if you operate at very high frequency, losses are also very high. So you have to balance between your losses and the induced EMF to see what is the optimum operating frequency for your transformer. For domestic appliances, they found that 50 hertz was found to be the normal frequency where the loss is also less, the induced EMF is also very high. But for certain application like aircraft and military, this 50 hertz was not found to be suitable. So they changed the frequency to 400 hertz. Okay, for domestic supply, we are going to use 50 hertz. For aircraft and military equipment, I'm going to use 400 hertz for operation. See here, employ 400 hertz power supply to reduce the core and winding weight. Okay, so different applications use different AC frequency for the operation, and that AC frequency what they use, they will have a significance for that. So for domestic appliances, we use 50 hertz to be the efficient frequency. For other applications like aircraft and military, I'm not going to use 50. It is not going to help me. So in aircraft, weight is a constraint. You have to minimize the amount of weight. So for that, 400 hertz was found to be suitable. So in aircraft and military equipment, they are going to use 400 hertz power supply to reduce the loss and binding weight. Okay, so there is no strict theory on which frequency you have to use to have maximum energy transfer. The frequency will be dependent on the application which you are going to use. Okay, so this same equation I can be using it for primary and secondary. In primary, I'll be using E1, N1. In secondary, I'll be using E2 and N2. That's the only change. So the same EMF equation, I can be using it for finding out the EMF induced in primary and secondary. See, frequency I told you will be constant, flux will be constant. So what is the only thing which is going to change? The suffix of E and N. So if you put E1, N1, it is going to be primary. If you're going to put E2, N2, it's going to be for the secondary side. So the same EMF equation, I'm going to use it for both primary and secondary of the transformer.